This video is on convolutional neural networks. So let's start by discussing what's wrong with how neural networks process images. Well, the fully connected network that we looked at previously takes in a vector as an input. And so we had to take the image that we wanted to classify and flatten it by stacking the rows together so that we could actually give it to this neural network as a vector. Now, for some problems, the order of the features in the example doesn't matter. For instance, if we have age, height, and hair length, for example, in a data set of people, but this isn't the case for images. If we randomly reorder the pixels in an image, then it will likely be totally unrecognizable. And that's because most of the useful information in the images comes not from the actual values which the pixel features take, but from their relative positions. And the same is true for any kind of spatially structured data, like videos, sound waves, medical scans, and 3D models, etc. And so the spatial relationships between different pixels is the information that's really crucial to the understanding of the image, and when we flatten that image, we lose that information. Another thing is that in computer vision, for example, we want to be able to do the same kind of, we want to be able to recognize the same kind of features regardless where they appear in the image. And this means that we probably want to use the same weights to extract that feature. But neural networks, they have individual features for every input feature because they expect them to all represent a totally different thing. And unlike in computer vision, that is, where different features can represent the same thing just in different locations. So instead of learning to look for the same features of an image with different weights for each position that the feature might be in, we should try to share the same learned weights over all the positions of the inputs. And this is going to save us both time and memory in computing and storing the duplicate weights that we would need to recognize some object in the left and the same object in the right. We just want to share the weights across the spatial structure of the input. And so this is what we're going to use convolutional neural networks for. So firstly, let's just remind ourselves of what do images look like as data. So they're obviously not naturally vectors. They definitely have a width and a height, but they also have, as long as they're not grayscale, they have what we call a channel. They have channels, and these channels basically represent the different intensities of the different colors which make up the colors that we see in these images. So yeah, basically any color can be made a combination of three primary colors. The three standard primary colors we use are obviously red, green, and blue. And so if we want to process an RGB red, green, blue image, that means it's going to have not only height and width, but it's also going to have these red channel, blue channel, and green channel, which specify the intensity of the greenness, blueness, and redness in each of these particular pixel locations. And so what we see is a combination of those three intensities. So they're not just matrices, they're actually tensors. They have three axes. And that's the case of images. So, quickly cover how was computer vision done before deep learning. What we'd have is people basically drawing the kind of features and things that they expected to be found in images and that would be useful for certain problems they wanted to solve. So they might draw something like this and say, okay, this filter that I've designed by hand is going to be useful for detecting faces. So yeah, they would draw things like these, which we call filters or kernels, and they basically look for a particular pattern, and that is they have high values where they have high values in kind of the shape that they're looking for. So here I've drawn a small example of a simple kernel or filter, is what you call these. And this one looks for vertical lines, and like I said, this one might look for faces. And so the way they look for these patterns they represent is by seeing how similar the pixels are at any location that they're applied on top of. A convenient way to do that is by taking a dot product, that is taking an element-wise sum. When we put this filter over a particular region of the image, how big is the element-wise sum of those different values in the filter and in the image. So if we have an image which has exactly this pattern underneath, well then we're going to have all of these high values multiplied, or these high red values multiplied by ideally high values in the image, and all of the pixel values around that multiplied by lower values. So what we'll get is a high value when this feature is mapped. Same for this vertical line one, and that's how we would kind of look for these patterns which these filters represent in images. So another thing to note is that in the case where we have a image with, or some other kind of data with different color channels or other different channels, then these filters will also have not only like a height and width, but they'll also have a depth. So they'll have these kind of patterns for the red channel, the blue channel, and the green channel. And it's standard for the depth of each filter to be the full depth of the input which it processes. So if this filter is going to be applied on a input with 3 channels, like an RGB image, then the depth of the filter would also be 3. And the pattern matching that's done by this filter would be contributed to by how well the pattern is matched for each different channel of the filter over each different channel of the image. So yeah, and the height and width of these filters are hyperparameters. They're up to us, but it's standard to have them with equal height and width. So now we'll talk about how we use these, and we're building up this understanding, so how we can use convolutional operations to build up convolutional neural networks. So in machine learning, convolution is the process of moving a filter across every possible different input and computing a value for how well it's matched at that location. So you can see here that happening. We've got this filter with these different values of these different weights of +1, -1, positive, minus, and so on. So we have these high values in an X shape, and this filter is being passed over this input and produces these different values for how well it's matched in each of those particular locations. And this gives us some spatially structured output from a spatially structured input. And what this represents, this output here, is how well was this feature mapped in any different location across the image. And we call this an activation map or a feature map because it represents exactly that. How much was the filter activated, and what features, was the feature present or not in these different locations. So we're just doing that dot product, that element-wise sum, that element-wise product, and then summing all of those up to get a single value from each different location in the filter of the filter on the input image. And so you can see that when the filter gets to this location there, it has a high value, has that 5, and that's because the pattern which is in the filter, this X, is also there, and that's why you get this high value there, and it's totally not matched. In fact, it's negatively matched there, and so you get a really negative low value. So we get down to there, highly matched here, very negatively matched there. And so this is just a simple example where our input only has one channel, but if it had multiple channels, then our kernel would also have the same number of channels, and the same kind of thing would be done all the way through all of those channels. So yeah, there's a few more kind of parameters that we can play with this convolution operation. One of them is the stride, and that's the step size of the filter when we move it. So here, the step size is 1. It could be different, and that would be the stride. If we have a higher stride, it means we have to do less dot products over each input. It means we do less computation, it might run faster, and we'll have to store less output values because we'll only be able to fit it, say, twice across there. If we had a stride of 2 in this case, we'd move the center from here immediately to here, and we'd only get a 2x2 output. Another thing we can do is add padding. So we can pad the input with extra pixels around the edge. Well, why would we want to do that? One thing is that because we're going to basically have this convolution operation as a layer in our model, and every time we apply it, the input gets smaller, there's a limit to how deep the model can be, because eventually we'll just end up with a 1x1 image, or 1x1 activation map, and we won't be able to convolve over that. But if we add padding, it means that we can make the input larger, so the output is also larger. and as such, yeah, we can increase the maximum depth of the model. Another reason that we might want to do it is because you notice here that these corner pixels, they actually this one only appears in one single, it only contributes to this feature, and the same for the others, they only contribute to the very extreme corner values of the activation map, whereas this input value here, this is actually in every single one of those, this actually contributes to every single value in the output activation map. So if we wanted to give each of the pixels in the input an equal opportunity to contribute to the output, then we could pad around the edges such that they would be included in more of the different feature mappings. So yeah, and then there's different padding modes that we can use as well. So we can either add zeros around the edge as padding. We can maybe reflect the final edge value outwards, or we can extend the value which appears on the edge outwards. And you can see all of those in the PyTorch docs, which I'll fix that link to. So here's just a visualization of the stride and the padding, and those things make up what the output shape is. So n, sorry I haven't written it down here, but n is the size of the height and width, which I've assumed to be the same of the input. K is the kernel size there, that K, and S is the stride. And this is the size of the output that we get. So you can see that as we increase the stride, we decrease the size of the output shape, and as we increase the kernel size, we also decrease the size of the output shape. But if we add padding, then we increase this value n, and that means that the output will be larger. And like I said, this means that we can increase the limit of the number of convolutional operations that we can apply successively to our input to process it. Cool. So yeah, and just point here for understanding is, for convolution, each computed value in the output feature map is a linear function of the pixels in a local region, so just this region, for example, as opposed to every single value in the whole image, which is what a fully connected neural network does. Every single output from a linear layer is contributed to by every single input from the layer before. But in convolution, it's only a local region which contributes to the output value. So here, it's only these values which contribute to this number here, not every single value in the input. And so yeah, now we can use this to make a convolutional layer, and what this is basically where we can just do the things we were talking about. So we can convolve filters over the image, and not only can we just do it with one filter, like with a regular neural network, we want to look for different features within the input. And so similarly with a convolutional layer, we can look for different features by convolving different filters which directly look for different things across the input, and each of these produce their own individual activation map. And what we can do is we can just stack these up to output a spatially structured output in the same way that the input is spatially structured. And then once we have this output, well then this is exactly the same kind of thing as this, and then we can convolve over this. So we can do successive convolutions. Note here as well that I've got an input of three channels here, and I've used four filters, and the number of filters, so each filter produces a single 2D activation map in the case of images, and then stacking those, well, the number of the number of channels of my output is the same as the number of filters I've used. So I could use way more filters than this, and then I would have, equivalently way more activation maps here. But then in the next layer, the depth of the weight of the filters which I use will be the number of activation maps which were output from the previous layer. So if we were to convolve over this output in another convolutional layer following this one, then our weights, they would have 4 channels, and each of the weights would take contributions from each of the different activation maps. So yeah, so like I said previously, it used to be in traditional computer vision that engineers would have to tune the filters of these weights manually, or draw them and try and understand, okay, what's going to be a useful feature for me to solve my particular problem in this particular domain. But now what we can do, similarly how we learnt the weights of our neural network model, we can just use backpropagation and gradient descent to find how we should update each of the weights in the filter so that our loss reduces, and probably the way to do that is to make it so that they look for successively more complex and more useful features. Another thing that we can mention quickly is pooling. And what pooling is a way to summarize the values which appear in some small region of an activation map. So we could, for example, have a 2x2 max pooling filter, and what that would do is it would go over the image like convolution, but instead of doing a weighted sum, it would just compress those 4 values into the maximum of those. Another thing we could do is take the average, and what this pooling does is it reduces the number of values needed to represent an output. So this can save you memory, and it can save you speed in processing that output. And it also means that we need to learn less parameters to actually convolve over that output or do whatever we want with that output if we're using some parameterized layer to process it after. Cool. So once we keep doing convolution, we're going to end up with something like this. But depending on the problem, we might want a different structured output. In our case, we're going to do the classification of MNIST. So what we want is a vector of 10. So we're going to need to somehow reshape this into a 10 vector. And what's pretty standard practice to do is to basically do some convolution and then say, okay, cool, that's my convolutional layers done. What I'm going to do now is I'm going to flatten those down, and then I'm going to apply some linear layer to transform however many values I have there into the number of values which I actually want to compute my output for, and hence a loss for. Cool, so we can implement that now. This is simply boilerplate that we've done already. It gets the data set, makes the data loaders, and then here we're going to implement and that's an example from the data set. Here we're going to implement our convolutional neural network. So in our torch.nn.sequential, which each of these is going to be, which returns us a callable object, which is going to apply each of these layers. The first layer we'll have will be torch.nn.conv2d, and the first argument which this takes in is how many channels does it take in. In our case, the input is an RGB, it's actually not, it's a grayscale image. So we've only got one channel in the input image. Let's say we want to use 16 different filters from that, and then so that's the number of channels that we're going to output, same as the number of filters, same as the number of things that we're going to look for in that image or in that input, and then we'll say kernel size of 5, something like that. Then we'll apply an activation function. Then we'll apply another convolutional layer. And so the input to this one, the number of channels which this convolutional layer is going to convolve over is the same as the output of the previous layer. So as I said earlier, so we're going to convolve through a depth of 16 activation maps, and then we're going to do that with, let's say, 32 different filters, and again we'll use a kernel size of 5. By default, if you give a single value here, it assumes that the kernel size has equal height and width, and that's what this number represents. Otherwise, I think you can pass in a tuple if you really wanted to have some kind of rectangular kernel. We won't worry about that. The next argument is the stride, and but it's optional, and you can check all of that out in torch.nn docs. Cool, so we'll apply second convolutional layer, and then we'll apply our final activation for our convolutional layers. And then we're also going to define our fully connected layers. So we'll get torch.nn.linear, as we have done before. And well, how many inputs is this going to take in? Well, I'm going to get the output of this and I'm going to flatten it, but I don't know exactly what value this is yet. So I can just put -1. It says, you know, do whatever you need it to be, and or actually, can I do that there? I'm not sure, but we're going to have 10 outputs right there. Yeah, I definitely can't do that yet. So I'm just going to put some value, which is definitely wrong there for now. And what it's going to do is when I try and run it, it's going to throw me an error and it's going to tell me it should be this value. And I'm just going to change it to that value. So firstly, we're going to pass this. So now we're going to define what happens when we pass our input into some input to our model, when we call our model on some input. Well, first we're going to apply our convolutional layers. So we've got conv layers up there. We're going to apply them on X, and then we're going to flatten it. So we're going to say x.view. Well, what's the shape it should be? This is going to be, it's going to be batch size by some number, but I don't know what that number is yet, so I'm going to leave that there. And then I'm going to do, I'm going to pass through our fully connected layers. So get the fully connected layers, FC layers, and apply that to X. And then we'll apply a softmax to transform that 10 vector into a probability distribution. So we'll say, we'll use f.softmax on X, and then the so remember the first dimension is for which batch, or sorry, is each example in the batch, and then for each of those we have a vector of 10 different values, which should represent our confidences for the input being a member of each particular class from 0 to 9, classifying handwritten digits. So we're going to apply this softmax to that dimension. So this would not be the rows, which would be each example in the batch, but it would be to the columns. So let's run that now. Where is this? 60. Yeah, so we just need a comma there. Cool, we've done that. Now we're gonna try, so we're gonna define our model, and don't know why it took so long. Now we're gonna try and train it. It's gonna give us that error. So cool, it's gonna say shape is invalid for input of size this size. So what size should it be? Yeah, so just up here, let's just do print x.shape. Cool, let me run that. This is the shape. So yeah, we got a batch size of 128. We've got our 32. We've got our 32 activation maps, and the size of them has been reduced to 20 by 20. So that's the height and the width, and this is the number of channels. So we want to reshape them into, it's going to be 32 by 20 by 20. Okay, so that's the number that should be. So I've just figured that out by printing this. Try and run it again, and we'll get the next error. So this one says, yeah, so this is what it's trying to take it to. So it should be 12,800. So we're going to change this number up here to 12,800. Then run this, and there we go. Now it's training and we've got all the sizes right. So that's going to go on to train, and then you can calculate the accuracy, and that's it done. You'll see that this is be able to easily perform just as well as our neural network, and should be able to do so with much less training time. So now you should understand the advantages of using CNNs versus vanilla neural networks, and how an image is represented as data, including the channels, what the convolution is in context of machine learning, and okay, don't worry about that, and the new convolutional pooling layers that we use in this notebook. Cool, yeah, this is only because I haven't moved my data to the GPU. Nice one.